So we invited Jonathan Baker, and I know that you studied meteorology in Reading, University of Reading, and did your PhD at the University of Exeter, and you are now working at the Met Office in Exeter.
Yes.
And you focus on the AMOC and how the AMOC responds to forcing, different kinds of forcing, and how stable it is. And we are really looking forward to your presentation.
Can you see that okay?
Yes.
Cool. Okay, thank you. Okay. Hi everyone, I'm John Baker from the Met Office, and thanks for joining, and thanks to ClimTip and the organisers for this opportunity. In this talk, I'm excited to share some of our recent findings about the Atlantic Meridional Overturning Circulation, or AMOC, which plays a large role in the climate system. And we'll explore how this crucial ocean circulation system could change in a warming climate and what that could mean for global climate. I want to acknowledge the collaboration between the Met Office and the University of Exeter, and a huge thanks to my co-authors for their invaluable contributions to this research. To begin, let's talk about what the AMOC is and why we should care about it. The AMOC is a large system of ocean currents, often likened to a conveyor belt. It transports warm waters from the tropics to the North Atlantic, where they cool, sink, and flow back southward. Now, why does this matter to us? The AMOC plays a huge role in regulating global and regional climates. It's especially important for Western Europe, where it acts like central heating, keeping temperatures much milder than they would otherwise be. And every 5 days, the AMOC transports enough heat to power the entire world for a year. That's a staggering amount. We expect the AMOC to weaken under climate change, and here's why. As the climate warms, the surface waters in the North Atlantic will become less dense. And this is due to both surface warming and increased melt of ice from Greenland's ice sheet and increased precipitation. And you can think of this process like a stack of pancakes. As the surface warms and fresh water flows in, it makes the top layers of the ocean less dense. And below these less dense layers, the ocean becomes more stratified, with denser layers stacking up underneath. And this makes the ocean more stable, like a pile of pancakes that resists sinking. The result, less sinking, less convection, and ultimately a weaker AMOC. Now let's consider the consequences if the AMOC were not only to weaken, but to collapse to a very weak state. Without the AMOC, we could see cooling across the entire northern hemisphere, while the southern hemisphere warms faster. And in particular, Europe could face the drastic temperature drop, with some climate models suggesting that annual average temperatures in London could fall by as much as 8 degrees Celsius, and even further in winter. However, it's important to note that these model experiments use freshwater inputs into the North Atlantic without accounting for background global warming. In reality, global warming would moderate the cooling effect. While most regions in the Northern Hemisphere would warm, the North Atlantic and Northwestern Europe could still experience cooling due to the shutdown of the AMOC, especially under lower end warming scenarios. And indeed, a recent study by Van Westen and Batson investigates the potential impacts of an AMOC collapse under global warming using the CESM2 model, with the collapse triggered by large freshwater forcing. Under 4 degrees Celsius of warming, they find the entire European continent warms as expected. However, the results under 2 degrees Celsius of warming shown here are striking. The model simulates a significant increase in cold extremes over northwestern Europe. For instance, Exeter in southwest England sees the number of freezing nights rise from 1 to 43 per year, and the minimum temperature observed every decade, shown by these contours, drops by 12 degrees Celsius compared to the pre-industrial control. Further north in Edinburgh, the impacts are even more dramatic. Freezing nights increase from 30 to 160 per year, and the minimum temperature observed every decade plummets by 22 degrees Celsius. And these experiments emphasize the potential severity of an AMOC collapse. But it's important to note that these outcomes will likely vary between models, highlighting the need for further research to better understand the impacts. The key takeaway is that a collapsed AMOC could dramatically alter regional climates, and this could mean colder winters for the UK, and yes, perhaps these scenes from Exeter and London from a winter snowstorm called the Beast from the East in 2018 could become the norm in UK winters. But the impacts of an AMOC collapse doesn't stop there. The global consequences would be far-reaching. Here you can see the effects of an AMOC collapse on global rainfall. The intertropical convergence zone, which drives tropical rainfall, would shift southwards, and there'd be altered monsoon patterns in the Amazon and parts of Africa. There would likely be much drier conditions in the UK and Europe, affecting agriculture, and there could also be a strengthening of the jet stream, increasing storminess. There could be accelerated sea level rise in the Atlantic region, especially along the US East coastline, and a reduced ability of the ocean to take up carbon dioxide. So an AMOC collapse wouldn't just affect Europe, it would have wide-ranging consequences for climate, ecosystems, and societies around the world. And even if the AMOC doesn't collapse, a weakening would bring many of these global impacts, with these impacts becoming more severe for a greater AMOC weakening. This is why policymakers need more accurate predictions to consider the potential risks when planning for coastal defences, agriculture, and water security. Given how crucial the AMOC is to our climate, there's growing concern about its future under climate change. The big question is, will it collapse? And if so, when? Here we define a collapse as a significant weakening, dropping the current AMOC strength by 65% to below 6 sphere-drips, and a complete collapse as a full shutdown to 0 sphere-drips. 1 sphere-drip is 1 million cubic meters per second. So at 17 sphere-drip, the AMOC currently transports 17 million cubic meters of water per second, or about 7,000 Olympic-sized swimming pools every second. The latest climate models from CMIP6, an international collaboration and modelling centres, project the AMOC will weaken this century, but there's a wide range in the amount of weakening across each of the shared socio-economic pathway, or SSP warming scenarios, with this shading showing the uncertainty. The IPCC's latest assessment states that an AMOC collapse is unlikely this century, but they express only medium confidence in this prediction, reflecting the large uncertainties that still exist in climate models. We know the AMOC has tipping points, critical thresholds beyond which the system could abruptly collapse, potentially in an irreversible way. And this was first demonstrated in a simple model by Stommel in 1961, and we've seen it in past climates such as during the Dansgaard-Oshkosh events of the last glacial period. And these events captured in Greenland ice cores show large transitions in global temperature, particularly in the North Atlantic region, with temperature changes of 10 to 15 Celsius over Greenland within decades. And these changes were likely caused by changes in the AMOC and in cycles where there's the rapid cooling by an AMOC collapse. However, Earth's conditions are quite different from those in the past. We now have a much warmer climate with less ice, different Earth geometry, and altered southern ocean winds. And these differences make predicting whether we'll cross a tipping point that would lead to an AMOC collapse complex. AMOC tipping behavior has been demonstrated in both intermediate complexity models on the left and in comprehensive global climate models like CESM on the right. Here you can see the North Atlantic freshwater input is slowly increased, weakening the AMOC until it passes a tipping point and collapses to a new stable off state. And we can think of the AMOC like a game of Jenga shown here. You're slowly pulling out the blocks one by one, and everything seems fine. The tower is still standing and starts to get a bit wobbly. But then, bam, one wrong move and the whole thing comes crashing down. You don't realize it's losing stability until it's too late, and then it's game over. The key difference is when the AMOC collapses, we won't be able to rebuild it with a few quick moves. Just like that Jenga tower, the AMOC stability hinges on delicate balances in ocean processes. While AMOC tipping points exist in these models, they suggest that a large freshwater input is needed to pass the tipping point. And this raises an important question. Are these models potentially overestimating the AMOC stability? Recent studies shown here, such as the work by Ditlevson and Ditlevson, have raised alarms about the possibility of an imminent AMOC collapse. Their statistical model predicts that the AMOC could cross a tipping point as early as this year, with a mean estimate around mid-century. And this has captured significant media attention. However, many researchers urge caution. The statistical methods, while useful, can sometimes give false alarms, a bit like a smoke alarm that goes off when you've just burnt the toast. The model also oversimplifies the ocean's complex dynamics, and there are large uncertainties in the temperature proxies they use to estimate past AMOC changes. Nonetheless, these studies highlight the real risks of an AMOC collapse, and the prediction can't be completely ruled out. A recent letter sent to Nordic policymakers, signed by around 40 climate scientists, argues that the IPCC may underestimate the risk of such a collapse. So the future of the AMOC is one of the critical questions in climate science due to the significant associated risks and uncertainty. With this context in mind, our recent research published in Nature gives a fresh perspective on the AMOC's future stability and comes to a different conclusion to these more alarming studies, one that's in line with the IPCC assessment. We focus on the upwelling pathways of the AMOC in climate models. These are the routes through which AMOC deep waters return to the surface. By examining these upwelling pathways, we can better understand what stabilizes the AMOC and what causes it to weaken. We suggest the AMOC might be more resilient than some recent studies have predicted, but that doesn't mean we're out of the woods. While a collapse probably isn't imminent, the risks of weakening are significant. We aim to answer a few key questions. What mechanisms prevent the AMOC from completely shutting down in most models, even under extreme climate scenarios? How do ocean circulations remote from the Atlantic, like those in the Indo-Pacific or Southern Ocean, affect AMOC stability? And ultimately, what does the future hold for the AMOC? To approach these questions, let's first define what we mean by AMOC upwelling pathways. These pathways describe how deep waters formed in the North Atlantic return to the surface through various processes. This classic cartoon by Broca shows the global overturning circulation, where deep AMOC waters formed in the North Atlantic return diffusively to the surface, mainly in the Indian and the Pacific Oceans. However, more recent research has highlighted the importance of strong westerly winds over the Southern Ocean, which act like a powerful pump, continuously upwelling these deep waters to the surface. So while the AMOC is driven by the densification in the North Atlantic, making it thermohaline driven, it also depends on these upwelling processes. And there's a significant wind-driven component from the Southern Ocean that we find is critical to its future stability. In this sketch, we see the present-day AMOC upwelling pathways. The Atlantic is at the bottom, the Indo-Pacific at the top, and they're connected through the Southern Ocean. There are 3 upwelling pathways of the AMOC's deep waters. The Atlantic upwelling pathway upwells and returns these waters diffusively in the Atlantic. The Southern Ocean upwelling pathway upwells these deep waters in the Southern Ocean, driven by strong Southern Ocean westerly winds. And the Indo-Pacific residual upwelling pathway upwells the remaining deep waters diffusively in the Indo-Pacific, before returning them back to the Atlantic via Southern Ocean zonal currents. And together, these upwelling pathways balance the AMOC's deep water formation in the North Atlantic. To quantify these pathways, we use a method adapted from my earlier PhD work, where we applied similar approaches to idealized simulations. Our method uses the overturning stream function, which represents the overturning circulation's volume transport. It allows us to track how much water is moving at different depths and latitudes in latitude depth space. And here the stream function is shown in the Atlantic on the left by the orange shaded stream function, and the Indo-Pacific on the right, and then averaged globally across the Southern Ocean. In the Atlantic, we see the AMOC's clockwise overturning circulation, whereas in the Indo-Pacific, the opposite happens with an anti-clockwise overturning. Our method is based on the simple idea that what goes down must come up and vice versa, since the ocean conserves volume. The AMOC Southern Ocean upwelling pathway is roughly equal to the strength of the Southern Ocean upper overturning cell at 34 south in the present day. But under extreme climate scenarios, we find a new clockwise Pacific overturning circulation, or PMOC, emerges in the Indo-Pacific, which reverses the current circulation in this region. Since the PMOC also upwells in the Southern Ocean, the AMOC share of the Southern Ocean upwelling becomes smaller than the strength of the Southern Ocean upper cell at 34 south. On to the results. We first explore the AMOC's behavior under extreme climate scenarios in CMIP6 models. For this, we use two experiments, one with an abrupt quadrupling of pre-industrial carbon dioxide to 1,120 parts per million, and another that uses a 0.3 Sverdrup, or 300,000 meters cubed per second freshwater input or hosing to the North Atlantic from the NA HOSMIT project. Here's a handful of the models. In the pre-industrial control experiment, we see a strong AMOC, while in the Indo-Pacific, there's an anti-clockwise overturning circulation. Under extreme scenarios, the AMOC weakens, and unexpectedly, a clockwise Pacific overturning circulation, or PMOC, emerges in the Indo-Pacific. And this is the future state, 90 years after the climate forcing begins. Here, the plot at the top shows the results from the 4x CO2 experiment, and at the bottom is the freshwater hosing experiment. On the left, the strength of the future PMOC varies widely across the different models. And meanwhile, in the Southern Ocean, the upper overturning cell at 34 south strengthens under CO2 forcing, whereas it weakens slightly under the freshwater hosing. Now let's look at the changes in the AMOC and its upwelling pathways under 4x CO2 forcing. On the left, every model shows AMOC weakening, but there's a wide range in how much it weakens. Looking at model projections of the AMOC is like picking the right movie night for a group of climate scientists. One wants a comedy, another wants a thriller, and the third, well, they insist it's a documentary about the uncertainties in climate model projections. Still, despite this widespread, out of the 34 models analysed, only 3 weaken below 5 Sverdrups after 90 years, and none shut down completely. In most of the models, both the Atlantic and the Indo-Pacific residual upwelling pathways shut down, leaving only the wind-driven Southern Ocean upwelling pathway. A key takeaway here is that since the AMOC strength is equal to the sum of these upwelling pathways, the future AMOC is sustained by the wind-driven Southern Ocean upwelling. Without this upwelling, the AMOC would probably completely collapse. So the future of the AMOC is directly tied to how strong the Southern Ocean upwelling pathway is in the future. As shown on the left here, the future AMOC strength is directly proportional to the future strength of the Southern Ocean upwelling pathway, because it's the only pathway that's left, except in these 4 outlying models. On the other hand, on the right, the Southern Ocean upwelling pathway in the control experiment doesn't explain the future AMOC strength because changes in this pathway vary across models. To explore this, we split models into two groups, those with stronger and those with weaker future AMOCs than you'd expect based on the control strength of their Southern Ocean upwelling pathways. Here's a key result. Changes in the AMOC Southern Ocean upwelling pathway depend strongly on the future strength of the Pacific overturning circulation, or PMOC. A stronger PMOC causes a greater decrease in this Southern Ocean upwelling pathway because both the AMOC and the PMOC compete for the same upwelling in the Southern Ocean, weakening the AMOC. On the right, the relationship becomes even stronger when we account for the change in Southern Ocean upper cell strength. So the future AMOC strength correlates strongly with the balance between the future strength of the Southern Ocean upper cell at 34 south and the PMOC. In other words, the future AMOC depends on three things: the current strength of Southern Ocean upwelling, how this changes under climate forcing, and how strong the future PMOC becomes. Since Southern Ocean winds which drive Southern Ocean upwelling are projected to strengthen under warming, the AMOC's resilience will depend on whether the PMOC becomes strong enough to offset the Southern Ocean upwelling. For the AMOC to completely collapse, the PMOC would need to be stronger than what we see in these models under extreme forcing scenarios. Now, what causes differences in the strengthening of the Southern Ocean upper overturning circulation across the models? Our results show no strong correlation between changes in the Southern Ocean wind stress or changes in the Southern Ocean buoyancy forcing and the strengthening of the Southern Ocean upper cell. This suggests differences in the Southern Ocean's eddy response are likely key to explaining Southern Ocean upwelling variations across models, with the role of eddy parameterizations and model resolution being crucial factors. Let's compare two models here showing how the AMOC and PMOC strength vary in the 4 times CO2 experiment. In both models, the future AMOC is almost entirely sustained by Southern Ocean upwelling, and they have similar Southern Ocean upwelling rates shown by the red line. But in the right-hand model, the PMOC, shown by the green line, is stronger, so it competes with the AMOC for more of the Southern Ocean upwelling, leading to a weaker AMOC, shown by the purple line. So what does this mean for the AMOC's future? Under the high-end SSP 585 scenario on the right, which by 2100 reaches CO2 levels similar to the 4 times CO2 experiment, the AMOC weakens by about 45% by 2100. However, in all models, it remains above the 6 Sverdrup collapse threshold, with a minimum strength around 7 Sverdrups. And crucially, it's sustained by the wind-driven Southern Ocean upwelling. Our findings suggest that the AMOC stability through the 21st century in CMIT models is maintained by robust physical processes in the Southern Ocean and the Indo-Pacific. So despite the alarming predictions, we argue that an AMOC collapse is unlikely this century, in line with the IPCC assessment, because Southern Ocean winds are projected to strengthen, and the PMOC, which could potentially offset the Southern Ocean upwelling, is generally weak or absent under realistic forcing scenarios. Let's move on to our 2023 study published in Geophysical Research Letters, where we explore the different shared socioeconomic pathway, or SSP warming scenarios, which are more realistic scenarios of potential future forcing. In these scenarios, we examine how the AMOC's upwelling pathways change throughout the 21st century, with the aim of constraining future AMOC weakening. In this plot, we show the changes in the AMOC and its upwelling pathways in the high-end SSP 585 scenario. We can see on the left panel the AMOC weakens in all models, as shown in the earlier slide. Both the Atlantic and the Indo-Pacific residual upwelling pathways weaken, while the Southern Ocean upwelling pathway remains fairly stable. Models with stronger historical Indo-Pacific residual upwelling pathways tend to show larger decreases in this pathway, which reaches 0 by the end of the century in most models. As observed in earlier studies, how much the AMOC weakens in each SSP scenario is correlated with how strong the AMOC was historically. Models with stronger historical AMOCs tend to weaken more by the end of the century, and the relationship is especially strong in the high-end SSP 585 scenario on the right. Let's take a look at how each of the historical upwelling pathways relate to the AMOC weakening. Specifically, the correlation with the Indo-Pacific residual upwelling pathway on the right explains 81% of the variance in AMOC weakening under the SSP 585 scenario. This correlation is much stronger than the 55% explained by the historical AMOC strength, reducing uncertainty in AMOC weakening by about 35%. And we see similar improvements under the low-end SSP 126 warming scenario. I believe this is the strongest constraint we currently have on predicting how much the AMOC will weaken this century. As the Indo-Pacific pathway reaches zero in most models by 2100, its historical pathway strength sets an upper limit on how much it can decline, helping to modulate the weakening of the AMOC. The decline in this pathway, driven by the warming and freshening of the North Atlantic, which reduces convection, is caused by two main factors. First, the weakening of the Indo-Pacific overturning itself, and second, the reduced overlap between the AMOC and the Southern Ocean's lower cell as the AMOC shifts to shallower depths, cutting off a major pathway into the Indo-Pacific. Although the other upwelling pathways also contribute to the overall changes in the AMOC, their relationship with AMOC weakening is weaker. So we argue that the relatively strong link between the historical AMOC strength and its future weakening is largely due to the Indo-Pacific residual upwelling pathway being larger in models that have stronger historical AMOCs. Since this pathway is a strong constraint on AMOC weakening, we use this constraint to estimate future AMOC weakening by using observation-based estimates from 3 global ocean reanalyses. These are GLORAN, ECHO, and a robust diagnostic simulation. And we also use the overturning estimate from the inverse model of Lumpkin and Spear. Using this plot from earlier, we match the Indo-Pacific residual upwelling pathway from each estimate to the x-axis and use the line of best fit to predict the AMOC weakening. The shaded area represents the 95% prediction intervals, giving us the uncertainty around these predictions. Typically, these observational datasets vary substantially in their estimates of the Indo-Pacific residual upwelling pathway. The pathway is close to zero in ECHO and the inverse model estimate due to a strong Southern Ocean upper cell, suggesting only a modest AMOC weakening of 30 to 40% by 2100 under the high-end SSP 585 scenario. In contrast, the pathway is much stronger in GLORAN and the robust diagnostic simulation, suggesting a strong weakening of around 60% by 2100. So based on these estimates, we predict that AMOC weakening will range between 30 and 60% by 2100 if emissions follow the high-end SSP 585 scenario, with uncertainty extending beyond this range. Interestingly, the historical AMOC strength predicts a 40% weakening by 2100, but the uncertainty in this prediction is similar to that based on the Indo-Pacific pathway, even though the AMOC strength is well constrained by the rapid observing array. Since our new upwelling pathway emergent constraint is stronger, improving our estimates of the Indo-Pacific pathway could significantly narrow the uncertainty in predictions of future AMOC weakening. To improve our predictions, it's crucial to enhance observations and modeling of the Indo-Pacific and Southern Ocean overturning circulation. A key part of this is reducing uncertainty in the present-day AMOC upwelling pathways to refine our projections. Ideally, we'd have direct measurements from an observing array in the Southern Indian and Pacific Oceans, similar to the Samba array in the South Atlantic. And this is high on my wish list, so if anyone happens to have a few £1 million lying around to fund an array, please let me know. joking aside, improving observations in this region is vital to improve our understanding of the AMOC's future. An array like this would allow us to directly monitor and estimate these circulations. We also need to refine our models, and to do this, we need to better understand what drives the PMOC and what model biases influence its representation. Since the PMOC could have significant impacts on climate and ecosystems, there's still a lot we need to understand. Our findings also offer insights into past AMOC changes when a PMOC may have existed. And we've shown in previous studies that the dependence of the AMOC strength on the Southern Ocean upwelling and the Pacific Ocean circulation has major implications for AMOC changes over millennial timescales, such as during the last glacial period. Further research is also needed to investigate how Southern Ocean eddy dynamics affect the changes in upper cell strength in the Southern Ocean and in turn influence the AMOC. To conclude, even under extreme climate forcing, Southern Ocean winds sustain a weakened AMOC. An AMOC collapse is unlikely this century because it would require a strong PMOC, one strong enough to balance most of the wind-driven Southern Ocean upwelling. Our findings not only challenge some of the more alarming predictions of a 21st century AMOC collapse, but also provide a more nuanced understanding of the AMOC's future, emphasizing the role of robust physical processes in maintaining its stability. While a collapse is unlikely, the AMOC is very likely to weaken this century, and these findings align with the latest IPCC assessment. We find the present-day Indo-Pacific residual upwelling pathway is a robust predictor of AMOC weakening, particularly under high-end SSP scenarios. But to improve these predictions, we need better observational estimates of this pathway, which would help narrow the uncertainty in future AMOC projections. The implications of this research extend beyond just understanding the AMOC itself. It's about improving our climate models, refining our predictions, and ultimately guiding more informed policy decisions, from mitigation to adaptation. The more accurately we can predict the future of the AMOC, the better we can plan for the associated risks, from rising sea levels to shifts in weather patterns. To enhance these projections, we need better measurements of the Indo-Pacific and Southern Ocean circulations, and this should be our priority for future research. This work has been published in GRL and Nature, and our latest study in Nature is all about balance, not only in the overturning vertical transports, but also in rebalancing the scientific and public debate around the AMOC's future. Here are a few media headlines that have followed our study, adding nuance to this ongoing discussion. The coverage has emphasized that while AMOC weakening is a serious risk, a collapse is unlikely before 2100. I'm very grateful for the overwhelmingly positive response to our paper from across the scientific community and for the healthy debate it sparked. This slide shows the broader media coverage our study has received. Our findings have been featured in a wide range of outlets, helping shape public understanding of the AMOC's risks and uncertainties. This media attention is crucial in ensuring the debate is grounded in the latest science. That said, while the Daily Mail might have turned our study into a real-life day after tomorrow, rest assured that a big freeze in Europe probably isn't imminent, though that doesn't mean it's impossible. The dramatic Ice Age-style shift in the day seen in the movie, definitely not happening. However, AMOC weakening alone this century could still bring significant climate impacts, in addition to the broader consequences of climate change. Our findings are not a green light for complacency, far from it. We must urgently reduce greenhouse gas emissions to minimize global warming and mitigate these risks. Thank you for listening, and I look forward to any questions you have.
Thanks very much, John, for this exciting and very clear presentation. I'm sure there are questions.
Thanks, Sebastian.
I see a hand by Thomas.
Oh, with all these participants, I'm already it's already my turn. Well, thank you very much for this great exposition and also focusing on physical mechanisms. I think that's really a complement which needs to be considered in eventually also in the assessment that is now ongoing in the IPCC. Regarding that, I was intrigued by your statement right at the beginning that while the surface becomes less dense due to warming fresh water from Greenland and increased hydrological cycle or meridional transport of water, this actually stabilizes eventually the water column. I was quite surprised because my understanding is that in the mid to high latitudes, you have the isopycnal outcropping, and so you can bring any change in density as a signal very rapidly and effectively into the interior of the ocean. Now, I was wondering whether perhaps we do not, or whether perhaps we underestimate the instability or the potential for instability in the current day ocean models that primarily use horizontal and vertical mixing parameterizations along with GM, and that this isopycnal process, which brings in buoyancy anomalies very effectively into the interior ocean, may actually change somewhat your conclusions.
Thanks, Thomas. Yes, I'm not sure what exactly I said at the start, but certainly didn't mean to infer that sort of fresh water added to the North Atlantic doesn't reduce the convection there. That's obviously what's driving the weakening in of the AMOC, and so that's the critical processes and the warming in that area too. And then our focus is more on the upwelling of those waters, and if those waters continue to upwell in the Southern Ocean, it has to downwell either in the Pacific or the Atlantic to balance that. So this acts as a stabilizing process in the system, but of course it's a balance between the North Atlantic push mechanism reductions in that and the pull mechanism that's continuing to pull it up. And so biases in models in those regions, as well as in the Southern Ocean, could definitely be important in either direction, I would say. So, you know, the eddies are more likely to reduce the strengthening of the Southern Ocean upper cell, but a lot of these biases could act in either direction, and there's a huge range across the models because of these processes in the upwelling vary so much. So yeah, a lot to improve in the models. Yeah, does that answer your question a bit?
Thank you very much.
Niklas?
Yeah, thanks, John. Very interesting. I have a question which is probably very obvious, and I think you're sort of by emphasizing a lot that sort of you're looking at until 2100. Could you elaborate a little bit? I mean, you know, we've all seen the drift out paper, but could you elaborate a little bit on how you feel, how the mechanisms that you identified as sort of stabilizing components, how they would play out also if one would look at longer timescales?
Yes, thanks, Nicholas. Yeah, really interesting study by Tridgefruit et al. and a similar related study by Van Westen in the last weeks that show the AMOC could collapse after 2100. And yeah, I think that's obviously really important and somewhat concerning that this could happen in SSP 126, the low end scenario. But I think there's only 9 models involved in this study. We need more long extended simulations to really properly evaluate those risks. in the SSP 585 scenario, most of them collapse, which is almost expected. The CO2 levels continue to rise well above 4 times CO2 into the next century. So it's more the lower end scenarios that are interesting. And I guess in those cases where it collapses, the convection in the North Atlantic and processes there are overriding the stabilizing processes in the Southern Ocean. And also perhaps the Pacific is changing more in those simulations. So that's something that I'd like to look into next, really. It sort of spurred me on to try to understand what's happening in those experiments from a pathways perspective. Because, I'm not sure is the answer, but it's clearly an increase in the risk next century. Thanks, Nicholas.
And Hubertus Fischer has a question.
Yeah, thank you very much, John, for a very interesting and clear presentation. As a paleoclimatologist, I'm of course interested, why do we have a complete AMOC collapse, for example, during the Heinrich events during glacial time? So what in your picture was different at the time that it was able to completely go down to zero?
Thanks, Hubertus. That's a really interesting question. And I think one point is that the climate was very different in these past climates. So perhaps colder climate with a lot more sea ice or a lot more land ice to start with. And so that can melt and cause that destabilizing of the North Atlantic, but by melting a lot more ice than is available today. Also, differences in the Earth's geometry. So the Bering Strait was closed during the last glacial maximum, at least, and that is thought to have helped collapse the AMOC because the fresh water can't escape into the Pacific, or vice versa, the fresh water in the Pacific isn't entering the Atlantic. So these differences might be important, and also the winds in the Southern Ocean are thought to have moved north or south during various periods in the past, and that may affect the Southern Ocean upwelling mechanism that is stabilizing the AMOC in these runs. So if the winds moved southwards, you could get a reduction in the upwelling there. But it's just really interesting question to understand why it's obviously happened in the past, but doesn't appear to be generally happening in the future, but could be happening after 2100. So yeah.
Thanks. I also have a question. The way I understood you, the fact that there's always wind forcing in the Southern Ocean, that requires some overturning somewhere, right? So you explained that the Pacific and Atlantic kind of compete then. And I'm not an oceanographer, but when you think of textbook explanations of the wind-driven circulation, that doesn't require any overturning, right? If you think of a subtropical gyre, for example, then mainly the movement happens at the surface, and then there's some lateral sphere transport. Why is it different for the Southern Ocean? Is it because the Antarctic continent is directly to the south?
Yeah, really good question, Sebastian. So in the Southern Ocean, there's no land masses to block the winds. So you have really strong winds, westerly winds there, going all the way around the globe. And that acts as a powerful pump, really, continuously pulling up these deep waters due to the Ekman transport, because it pushes the waters to the north at the surface, and that pulls waters up from the deep ocean. So much deeper than like what you see in the subtropical cells. There's not this continuous movement of really strong winds all the way around the globe. and that's why the sort of the isopycnals slope up to the surface then in the Southern Ocean. So yes, it's slightly different at those southern latitudes because of that.
Yeah, okay, I see. Thanks. And maybe another one. There are some of these Earth system models, they do have alternative AMOC states, right? How
they do have what? Sorry?
They do have alternative, they have multi-stability. And how do they fit into the message that the AMOC cannot fully collapse?
So that some Earth system models have been shown to have tipping points. Is that your sort of question, and sort of collapse to an off state?
Yeah.
Yeah, I mean it's certain that there's tipping points are possible in these models if you force them enough. And a lot of the experiments which do collapse the AMOC via tipping points sort of add huge amounts of fresh water to the North Atlantic in order to force it to tip, because the models are not are either overstable or perhaps stable for the correct reasons. And so you do need to push them hard, and then you can get the collapses in the AMOC. And I guess that's one of the big questions is, are the models overstable or not? Yeah. And those tipping points have been known since, Stommel in 1961.
So in the SSP simulations that you analyze, that doesn't happen. That's the point. Yeah. Okay, thanks.
No. I mean, I think it's hard. The sort of recent study that came out suggests that tipping points could be crossed this century. And I think that's something that you can't disprove or prove correctly unless you sort of reverse the forcing in those experiments. But I think in most of the SSP runs, other than the high-end runs, they generally don't cross those tipping points because they don't collapse later on.
Thanks. Any more questions? We still have some minutes. Now is your chance. Yes, Ayako.
Hello. Thank you very much for your nice talk. Southern Ocean and around Antarctica, it is quite difficult to get the temperature, sea ice, and the wind right. And how does this bias compared to observation of each model affect your result, or this tendency, the relation that you found?
Thanks, Ayako. Yes, so we haven't looked specifically at how the sort of temperature and ice vary compared to observations in each model. I think the key process really is further north than where the sea ice is. So we're not so interested in the Antarctic bottom water formation. We're more north of that, sort of 35 degrees south. And here the winds are the key mechanism in terms of the dynamics, along with eddies, which are going to reduce that upwelling cell. But of course, temperatures, salinities in this region would also be critical. But yes, we don't go into specifics model by model. That would be interesting to understand more. But yeah, there's this huge range across the models, but in all of the models, there's this, under the SSP 585, they don't collapse this century, because in all of the models, there's enough upwelling in the Southern Ocean to keep it going at least this century. But yeah, that would be interesting to understand.
Thank you very much.
Thank you.
And any remaining questions? Yeah, Thomas?
If I may, just recalling, about 20 years ago, people used to carry out experiments with two basin models that were connected with an ACC, sort of very schematic models, but using 3D, even eddy resolving models. Do you plan to look at simpler geometries to really flesh out the mechanisms even more profoundly than what you have presented?
So yeah, I think the simpler models have a really important role in being able to understand the mechanisms more. And actually, we came at this from that place. So during my PhD, we actually used the two basin models with the Southern Ocean Channel, and from that, but looking at sort of past climates and long equilibrium simulations. But a lot of the mechanisms are similar in those runs to the transient timescales, which was maybe not completely expected, but the similar processes like the shoaling of the AMOC still reduces the pathway into the Indo-Pacific and leaves the Southern Ocean upwelling. But there's certainly a lot more experiments that you could do in those sort of simple models. So it would be nice, but I don't have that model running anymore, so it would have to start from scratch almost. But yeah, that would be nice.
Thank you.
Thanks, Thomas.
And next is Ent.
A quick question from an uninformed person. I didn't see the cold blob in the North Atlantic featured in any of those slides. Perhaps you're running just from models and therefore not relevant. Thank you.
Yes, so we didn't look at the temperature changes in the North Atlantic, which, as you say, as the AMOC weakens, it is expected that the sea surface temperatures in the North Atlantic could reduce, depending on how strong the warming scenario or how high emissions are into the future. But that's, so in these models, it's possible that the warming hole shows up as the AMOC weakens, which would depend model to model, and other processes such as the atmosphere could also be important in that.
I suppose my question relates to observational data around that cold area, and you've said, well, I'm not clear on the relationship of observational data to these models, but let Victor ask the question, please. Thank you.
Thank you.
Hello, thank you for your presentation. I'm not sure if this was answered already, but I wanted to ask about the Southern Ocean upwelling strength and the strengthening of it in the high greenhouse gas emission scenarios. How certain is this, and are there any biases that could kind of change this conclusion?
Yes, that's a really good point. The Southern Ocean upper cell does tend to strengthen in warming scenarios, especially under the higher end warming scenarios, less so in the low end. And that that's due to strengthening of the Southern Ocean winds. And if the sort of eddies aren't properly resolved or aren't properly represented in the models, then that strengthening of the Southern Ocean upper cell could become less than in these models. and obviously as we go to higher resolutions, hopefully that the eddies will be better resolved. And we do see some difference in the strengthening of the Southern Ocean upper cell between models which have 2 resolutions in their family, so that they do tend to be slightly weaker strengthening in the models that have higher resolution, but they still strengthen in those models. And so the results aren't majorly affected by that. But yes, that's one of the biases that could be important, and hopefully that will be improved in future models. Thank you.
Thanks a lot for joining, and thanks, John, again for the insightful discussion and presentation.
Thanks, Sebastian, and thanks everyone for joining and for this opportunity to share our research.